So today we're going to look at composite functions. When a new function is composed of two or more functions where one function is inserted into another function, this is called a composite function. And we often express this in two ways. So when I write f of g at x is equal to f bracket g bracket x close bracket x, what we're saying is that g is inserted into f at x. So g at x is inserted into f at x. And this is read as, I should say, f of g at x. So whatever function is on the outer side of the bracket, right? So to the right of the O, that is going to be the input. Okay, so that's what you're inserting into. Now, if I wanted to go the other way and I want to write g of f at x, then I would go like this. I would write g of f and then at x. And then that would look like this, g f at x like follows. So in this case, right, this one is to the right of the bracket. So this is the input. When it's portrayed like this on the right here, so I'm going to underline this here, whatever letter is inside the first bracket, that's of course going to be the input. So in this case, it's the G, and then the F is the letter inside the first bracket, so that's the input as well. So given that f at x is equal to 2x squared minus 1 and g at x is equal to 3x minus 4, find g of f at x. So for this one here, remember that this is going to be the input. So I'm going to first write the other notation, which is g at f at x. And then that's going to be equal to, so when I write g at f at x is equal to, I'm going to write 3x minus 4. And then this function over here is going to be placed inside the x. So then that's going to go 3 and then 2x squared minus 1 close bracket minus 4. And then I'm going to apply the coefficient to everything inside the bracket and then simplify it. And when I do that, I end up getting 6x squared minus 3 minus 4, which of course is going to reduce into 6x squared minus 7. And this is the expression for g at f at x. Now for the next one, we're going to switch it up. It's going to be f of g at x. So that notation is going to be f open bracket g and then at x. And so what we're going to do is we're going to write f at g at x is equal to, and we're going to write 2x squared minus 1. And this equation is going to go into the x over here. And when we do that, that's going to be 3x minus 4 squared minus 1. And like I did previously, we're going to apply the coefficient to everything inside here. And actually, what we should do is expand this first. So finally, after all the distributive property and the simplification, we get that f of g at x is equal to 18x squared minus 48x plus 31. Now, you're also allowed to, and this might be a little bit tricky to some, but you're allowed to substitute a function into itself. Okay, I mean, that is theoretically possible. It's unusual, maybe to some, but it can be done. And so let's say we ask for g of g at x. So we're taking one part of g and substituting it into, itself. So we would simply rewrite it kind of like this. So it'd be g at g of x. And then when I would write the formula. So it's an input into itself. So we would go g of g at x is equal to 3x minus 4. And then we're going to plug in the 3x minus 4 into the x. So 3x minus 4 minus 4. And then the rest is, well, just like we did before, where you have to do the distributive property. And when we do that, you end up getting 9x minus 12 minus 4, which then, of course, will simplify to about 9x minus 16, and that is the g of g at x. Consider the functions f at x is equal to x squared minus 3 and g at x is equal to root x minus 1. Let's say this time I want to actually find the values, the total output of the new composite function where f of g at 2. So the first thing I'm going to do is I'm going to get the actual function of f of g at 2. So substituting g into the f function here, I end up getting root x minus 1 squared minus 3, which we know that these cancel out. And then I'm left with x minus 1 minus 3, which when I plug in the value of 2 into the x, right, because remember that this is now f at g at 2, then we're going to go 2 minus 1 minus 3, and that gives me a total value of negative 2. For the next one, where I'm doing gf at f at x, which is equal to x minus 1, I'm going to substitute x squared minus 3 into the root x minus 1. And when I do that, I get this expression, which really can't be simplified anymore. So now what I'm going to do is I'm going to plug the 0 directly into the root. Now, once I've plugged in the 0, because that's the original input, right, over here, I'm just going to circle it here, I got to a negative under the root. And we know that the negative is a non-permissible value under the root, because you can't have a perfect square where one of them is negative and one of them is positive to give that negative product. It's impossible. So what we would say is, in this case, we would just say that this does not exist. So let's say we're asked to describe the domain and ranges of composite functions. We're going to follow a similar suit to how we were solving them previously, which is we're going to complete the composite function. And once we have that composite function and we understand what kind of function that composite function is, meaning does it fall into the quadratic category, is it a root x, or a general root x kind of equation, then we can figure out the domain and range of the new function. So using the functions previously stated here in the video, where f at x is equal to x squared minus 3 and g at x is equal to root x minus 1, let's say I wanted to find the domain. So we're going to write the domain of f of g at x. Once we've established the composite function of f of g at x, then a couple of things can tell us, and mainly one thing can tell us about the domain is that we have a root function here. And what we know, I'm going to write a little note here, is that you cannot have a negative under the root. So what that means is any value of x that is going to make this root value less than 0 would not be allowed. Therefore, we can say, since it's x minus 1, that x must be greater than or equal to 1. Because if it's equal to 1, you'll get a value of 0 underneath the root. So, other than that, we can say that for all values of x, where x is greater than or equal to 1, and x is all real numbers. And it can be any value that is greater than 1, and it can go up to infinity. This graph doesn't have any other limitations that way. So this would be the domain over here. Now, with the same idea for the range, well, we have the d value. Since this is a radical function, we have the d value of the transformation here. And what this value does is it tells you its minimum vertical value, or where the graph will start vertically. So then what we could also say is the range for all y values such that y is greater than or equal to -3. And then y is equal to all real numbers as well, because it can be anything greater than -3. Furthermore, when we graph this equation over here, we can see that it begins right at -3 on the y-axis and then keeps going to the right and upwards at infinity. And with regards to the x-axis, it begins at 1 and then keeps going this way. So it's greater than or equal to 1 for the domain and then keeps going, and greater than or equal to -3 and keeps going. So even if you plug this into your calculator, you're going to get the same results. But the key is getting the parent function or the new composite function.